Let us now move on to the next problem, problem number 21. Problem number 21. Let's see. Okay. Okay, so let's see what it states. Problem number 21 says a thin conducting square loop of side L is placed in the first quadrant of the xy plane with one of the vertices at the origin. So it says thin loop, a thin square loop. Let's draw. Let us draw the coordinate axis first. Let this be x, this be y, and if you apply the right hand rule, and then this should be called z, and the square loop is placed in the first quadrant of the xy plane with one of its vertices at the origin. So this is one of the vertices, and it is of side L. Now it says that there is a changing magnetic field that is applied. The magnetic field looks like this. It's a function of x, y, and z. It says phi of y, z, t, x cap plus z, x, t, y cap plus 3y squared d z cap. Beta 0 is a constant, and this is the full magnetic field. You see it has components in all the directions, and all you have to find is what is the magnitude of the induced EMF. So you know that the magnetic field is changing with time. So according to Faraday's law of electromagnetic induction, it has to induce an EMF in the square loop, and following which it can induce a current. Now, the EMF is simply given by d phi of dt. And where epsilon is the induced EMF, phi is the flux. What is the flux? How do we calculate flux? Flux is nothing but magnetic field times the area vector. The area under consideration, basically the flux through the area. You see this area vector. The area vector has to point along z direction here. The area vector has to point along z, and so the area vector is the area, which is L squared z cap. So now if we have to calculate phi, we find that it is basically beta naught times L squared, and you see A has only component in z direction, and if you take a dot product of B with A, only the z component can survive, because x cap dot z would be 0, y cap dot z would be 0, because they're all perpendicular unit vectors. So the only component surviving is 3y squared t. And therefore d phi of dt, which is EMF, you take away the d term, it's about 3y squared, and the y here has to be taken equal to L. Y equals to L, because that's where one of the sides of the square loop lies. If y is 0, d is 0 for this case. If it's all 0, epsilon goes to 0, but y equals to L, the induced EMF. So it's about beta L squared times 3 L squared. So 3 beta L to the power 4. That that is our answer. 3 beta times L to the power 4, 3 beta naught times L to the power 4, which is option B. This concludes our problem of the EMF. Induced EMF in a squared loop. Simply have to apply Faraday's law and basically take note of the geometry. Let's move on to question 22. Let's move on to question 22, which gives you two decisions. So this is a question about quantum statistics. So it gives you two distributions, the two famous distributions of quantum statistics. So this one is the Fermi-Dirac distribution. This is the Fermi-Dirac distribution, which is 1 over exponential raised to e epsilon minus mu over kT plus 1. Epsilon is the energy, mu is the chemical potential, or in this case it is actually the Fermi energy, and kT is the temperature. And the other distribution is, as you guessed it, it's the Bose-Einstein distribution, which is pretty similar, except in the case of plus 1 we have minus 1, and here it's epsilon minus mu over kT, and mu here is interpreted as the chemical potential. So now what is asked is, in which of the following limits does these two distributions reduce to the Maxwell-Boltzmann distribution? In which of these cases will it reduce to, which of the limit will it reduce to the Maxwell-Boltzmann distribution? What is the Maxwell-Boltzmann distribution? Let us write it down. The Maxwell-Boltzmann distribution is actually just a negative exponential, a decreasing exponential. We call it sometimes the Boltzmann distribution, and sometimes we call it the Boltzmann distribution. In this case, we are calling it the Maxwell-Boltzmann. Now look at the two distributions, the quantum distributions, and notice carefully. Where can we actually take the limit? It's the exponential factor, because everything else is a constant. One is constant. The only thing that we have is this exponential. And notice that if we can ignore this one factor, and we simply have 1 over exponential raised to e epsilon minus mu over kT in both cases, and that would basically give us the negative exponential that we're looking for. So under what conditions can we ignore the 1? And the condition would be that if this term is much greater, if this term is much greater than 1, then both in F, Fermi-Dirac distribution, the Bose-Einstein distribution, will tend towards the Maxwell-Boltzmann distribution. And typically, when can you do that? We can do that. The exponential becomes large when its exponent becomes large, which means when epsilon minus mu over kT becomes very large, or which implies when epsilon minus mu becomes much larger than kBt. This is our condition, and that is our option C. So when epsilon minus mu becomes much larger than kBt, both the Fermi-Dirac distribution and the Bose-Einstein distributions are reducible to the Maxwell-Boltzmann distribution. And that concludes such problem number 22. That was a quick one. Just elementary reasoning involved. And now let us move on to problem number 23. It says, consider n classical particles at temperature T each of which can have two possible energies, 0 and epsilon. So it's a two-level system that we're considering. One of them has energy of 0, the other has energy of epsilon. And there are n particles. These n particles can occupy either the 0 state or the epsilon state. Nothing else. It's a two-level system. It's what we call in physics two-level system. The number of particles in the lower level n naught, let's call the number of particles in the lower level to be n naught, and the number of particles in the higher level to be an epsilon correspondingly, such that n0 plus n epsilon has to be n. How are they related? This problem really doesn't ask for any calculation, but if it says it's classical particles and the temperature is T, so we know that we have to apply classical Boltzmann distribution. The distribution we are looking for is NMB, and the distribution we just saw, in this case it would be epsilon minus 0 by kT, which is epsilon by kT. And so here NMB, and here, so if you are considering number of particles in epsilon state, the ratio of it with respect to number of particles in the ground state would be simply this, and that is all it asks for, ratio 2. So and the answer is slightly, the option B suits it, because if you invert this ratio, the negative exponential becomes positive exponential, and that's what it asks for. That is all it asks for, and that is our option B. So that concludes our problem number 23 as well. All we had to do was apply the classical Maxwell-Boltzmann distribution. Let's move on to problem number 24.